teacher Fab, and today we'll talk about Coulomb's Law. So, in electrostatics, we learned that when an object gets an imbalanced charge, it will produce a static electricity. When I say imbalanced charge, that refers to the object gaining um, electrons or losing electrons. So, the object can be positively charged, or the object can also be negatively charged. When the object becomes positively charged, that means that the object loses electrons. Okay, so this one, it loses electrons, and when the object becomes negatively charged, that means that it gains electrons. Let's say, for example, we have two balloons. So we have balloon one and balloon two. Let us say you charge the two balloons. You rubbed them. Okay, this is charging by rubbing. Okay? You rubbed them with your hair. You also rubbed the second balloon with your hair. So what happens to the first and second balloon? They get an imbalanced charge. They become both negatively charged. Okay, and balloon two also become negatively charged. Your hair becomes positively charged. So this is based on the triboelectric series or the rank that there is more tendency for your hair to lose electrons compared to the rubber balloon. And the rubber balloon has more tendency to gain electrons. So electrons are transferred from the hair to the balloon. So that's why it becomes negatively charged. So when you place them near each other, the first and the second balloon, they repel. They move away from each other. So we can observe a repulsion because they are of the same charge. So like charges repel. However, if you have another scenario that we only rubbed one balloon with your hair, so let's say this is the first balloon, this is the second balloon, and you rub the first balloon with your hair, you just ignore the second balloon, just to leave it as it is there. Um, the first balloon becomes negatively charged again. Okay, so it becomes negatively charged. Your hair becomes positively charged. Again, this is based on the triboelectric series. That your hair has a tendency to become positively charged compared to the balloon. Okay, now when you place this first balloon near to the second balloon, you will observe that they get attracted to each other. So there is a force of attraction between these two balloons. So what happened here? Why is it that the second balloon becomes attracted to the first balloon? It's because in the second balloon, there is what we call charge separation. Okay, there is a separation of charge here that happens. The moment that you place a negatively charged particle or object near to a neutral charge, if I say neutral, that means that the number of protons here in the second balloon and the number of electrons are the same. So they are of equal charge. That's why the whole charge of the object is neutral. Now, when you place an electrically charged object, negatively charged object to a neutral object, there's a separation. So the positive charges here inside this balloon moves to the side. Okay, it moves to this side, while the negative charges moves to the other side. So hence there's a separation of charge. That's why it gets attracted. It gets attracted to the first balloon, so they attract. Before before the 18th century, they cannot quantify the force of attraction or the force of repulsion between these. So there's really a question as to how strong the forces are between these two objects, how strong the repulsion, the force of repulsion is between these two objects, and what are the factors that affects these forces. Not until the 18th century that Coulomb's law is discovered or is proposed. So who proposed Coulomb's law, and um, what are the factors that can affect the forces of attraction and the forces of repulsion between these two electrically charged objects. So let's take a closer look on the Coulomb's law. So this is proposed actually by Charles Augustine de Coulomb. Charles Augustine is a physicist, um, and in his experiment, he is able to really quantify or measure the force that's acting on two electrically charged particles. Let's go back to the two particles here. So let's say these two objects or two particles are electrically charged. So let's say this one is positively charged, this one is negatively charged. And we denote the charge as Q. So Q1. It can also be a capital Q or a small q. And let's say this is Q2. The charge of separation is the separation is denoted by R, which is the distance. Okay? The distance between these two charges. According to Coulomb, in Coulomb's law, um, the electrostatic force between these two charged particles is proportional. Okay, this is the proportionality constant, proportional to the product of the two charges. Okay, and inversely proportional to the square of the separation or the distance. Okay, so here we can say here that there is a force or there are forces that governs this kind of interaction between the positive and the negatively charged particle. So here we can say that they attract. Um, the first particle and the second particle here exerts. They actually exert force towards each other. So if we're going to draw the free body diagram, this is the force 1 to 2. So this is the force that is exerted by object 1 to object 2. And this is also the force that is exerted by object 2 to object 1. Here, the force exerted by the second object to the first object. Hence, it's attracted. Um, Also, this is the force that is felt or that is experienced by object 2, which is exerted by object 1. So this is the Coulomb's law. Fe, or the electrostatic force, is equal to the proportionality constant or the electrostatic constant times the product, the magnitude of the product of the two charges. You have your Q1 and Q2 over R squared. So we get here an absolute value. So this one is an absolute value because we are just getting the magnitude. So this means that whenever we increase the distance, we will have a decrease in the value of f. Whenever we increase the distance, we decrease the value of f. So let's draw that. Let's say we have here two charges and they are separated by r, and the f here is f1. Now let us compare it with the second scenario wherein the distance is larger, or it's wider now. It's farther. The separation between these two charges is farther. So we have here Fe2. So in this case, we can say that Fe1 should be greater than Fe2. So the closer they are, okay, the closer the particles are towards each other, the bigger or the greater the force of attraction or repulsion is. The farther they are from each other, the smaller the force of attraction they will feel towards each other. It's either the force of attraction or force of repulsion. In this case, we have force of attraction because they are of different charge. Okay? And take note that K here is a constant, so it has a value that is fixed. That's approximately 9 times 10 to the power of 9, and the unit is Newton meter squared over Coulomb squared. Okay, and our Q here is in terms of Coulomb. Our Q also here is in terms of Coulomb. And our distance here is in terms of meter. Now, when you square it, it should be meter squared. So if we look at the units, there are units that we can cancel to get to arrive at the final unit for the electrostatic force. So we can cancel the Coulomb squared. We can cancel also the meter squared. So we have left is Newton. Newton, which is the unit for the electrostatic force. Okay, so let us try a problem for this. Let's try to solve a problem applying the Coulomb's law. So let's say, for example, we have two charges. Okay, the first charge is um, positive 4. The second charge is negative 2 Coulomb. Okay, let's draw that. Let's say this is positive 4. So Q1 is equal to positive 4 Coulomb. And Q2 is negative. So Q2 is equal to negative 2 Coulomb. Let's say they are separated by a distance of 20,000. So R is equal to 20,000 meters. Mhm. So what is our electrostatic force here? What is the force that is experienced by object 1 by object 2? What is the force that is experienced also by object 2, which is exerted by object 1? So let's say we have Fe, so they will feel exactly the same force. So Ke times the absolute value of Q1, Q2 all over R squared. Let us substitute the values. Fe is equal to 9 times 10 to the power of 9 Newton meter squared per Coulomb squared times the absolute value of Q1. Our Q1 is positive 4 Coulomb. Our Q2 is negative 2 Coulomb. Yeah, we get their absolute value. That means that the answer here is positive always. Because again, we are just getting the magnitude of the electrostatic force. All over R squared. What's R squared here is 20,000. 20,000 meter, and we get the square. So using our calculator, what should be our answer here? Fe is equal to, so let's our calculator. It's 9 times 10, so 9 exponent 9 times, here we enclose it in the parenthesis, 4 times 2. So I did not write the negative because we already know that it should be positive answer here. And we should divide it with the square of the distance, which is 20,000 meters. So that's 20,000 squared. Okay, 20,000 squared. And so our answer is 180. Okay, so 180. Now the unit should be in Newton because then again we can cancel the column. We can also cancel the meter squared. So it should be meter squared. So the final answer for the electrostatic force is 180 Newton. What if we are given a problem that it will ask us to solve for the charge, not the electrostatic force? So let's try. So you are given a problem wherein you are going to solve for the charge, but not the force. Let us say two equally charged spheres. So two equally charged spheres. So there are two equally charged spheres. Mm, can you? So let's have Q1 here and Q2. Now they are equally charged. So therefore we can say that Q1 is equal to Q2. And let's just denote this with Q. Two equally charged spheres exert 12 Newton to each other. So the force here is equal to 12 Newton. And the distance between them is 12 meters. Let's just say 12 meters. So the question here is um, calculate the charge on either sphere. So what is Q1 and what is Q2? So it should give us the same answer for Q1 and Q2. So for us to solve this one, we will use again the Coulomb's law, wherein F E is equal to K E times the absolute value of Q1 Q2 over R squared. So since Q1 is equal to Q2, so we can just multiply them. We will use Q here instead. So Fe is equal to K E Q squared. So this time it's Q squared because when we multiply Q and Q, that's Q squared over R squared. So for us to get Q, we should transpose the equation. Some of the um, constant, it should be transposed here below, and R squared should be transposed here to the left side. So let's just use this Q squared. Okay, Q squared is equal to Fe Fe times R squared over Ke. Okay, so we transpose Ke below and we transpose R squared here. So we should multiply Fe times R squared over Ke. I just interchange the places. Okay, we can just interchange them. And then for us to get Q, we will square root. So this one will cancel, we will have Q. So this becomes Q is equal to square root of Fe R squared over Ke. And so Q, substituting the values. So square root of 12 Newton times our R is 12 meters. So 12. So our R is this one, 12 meters squared all over KE. KE is constant 9 times 10 to the power of 9 Newton meter squared per column squared. Okay, so Q, if we're going to use our calculator in that, so first we got 12, okay, 12 times the square of 12 meters. So here, 12 squared, okay, that's 1,728 divided by the 9 times 10 to the power of 9, our constant, 9 exponent 9. So in the calculator, you can just uh, do that right away. 9 exponent 9. Okay. So that should be 1.92 times 10 to the negative 7. Need to be negative 7. But we need the square root. So we need to get the square root of the answer. That should give us 4.38 times 10 to the power of negative 4. What's the unit? That should be in column. Okay, so our Q is equal to 4.38 times 10 to the power of negative 4 column. Therefore, our Q1 should be the same. So we should have the same answer for Q1 and Q2. So this is also equal to Q1, Q2, which is equal to that one. Now, 4.38 times 10 to the power of negative 4 column. Okay, so this should be our answer. Okay, so I hope you understand this part. So going back to our Coulomb's law equation, if we are given with force and the charge, we can actually solve for our distance of separation. If we are given with the distance and the force, we can solve for the charge of either of the sphere. Um, if we are given the charge and the distance, we can also get the force. Okay, so I hope you understand and you learned something from this review. So about Coulomb's law. There are other problems in Coulomb's law that it will not only involve two spheres, but it will involve more than two spheres. So in that case, you will have to use the superposition law for that, and that will take us to another um, video review. Okay, so thank you for your time. You have a great day, and I hope you learned something. Bye bye.